Hi everyone, thanks for joining us for the January 2DCC webinar. Today's speaker is Dr. Fei Yao from the University at Buffalo. And Dr. Yao, you're good to begin as soon as you're ready. Thank you.
All right, thank you. So the slide is advanced, right? Let me come to this. All right. Hello, everyone. Hi, my name is Fei, and I'm currently assistant professor at the Department of Material Design and Innovation at University of Buffalo. And it is my great pleasure to be here today. And I would like to thank the organizer for the kind invitation. So today we will discuss this two-dimensional van der Waals material for electrochemical applications. All right, let's start. So I'd like to give a quick introduction about my lab at UB. So we're working on low-dimensional material synthesis, property engineering, and their applications. For the material synthesis, we use wet chemistry method as well as chemical vapor deposition, CVD method. So in terms of the solution-based synthesis, we can produce the low-dimensional material such as zero-dimensional hollow carbon nanosphere, one-dimensional nanotube. Actually, this is coated with silicon, and also 2D materials. For example, here's the MaxSyn synthesized by a solution-based technique, and we can produce powders, thin films, as well as suspensions. As for the CVD synthesis, we produce atomically thin, high-quality graphene as well as transition metal dichalconide. And using these materials, we target for different applications. For example, the electrochemical applications, which is the topic for today, we leverage the wet chemistry synthesized material to be used as a catalyst for electrocatalysis. So basically, we aim to replace the noble metal by using two-dimensional materials. Also, this kind of bulky structured 2D materials through the wet chemistry method can produce those samples which are can be used for the battery applications. And those are some examples in my lab that we worked on for the battery anode application. So we're also working on the post-lithium batteries, such as sodium or potassium batteries, which is also the big thrust in the field. So in addition to that, we're working on some electrochromic device. Basically, this is a dual functional device. So as you can see, the color of the device will change upon applied voltage. So basically, it works like a smart window. And simultaneously, this device can function as a battery, as evidenced by this particular figure. So this multifunctional device will be useful for energy efficient building as a smart window. As for the CVD synthesized material, we are interested to investigate them as a channel material for the energy efficient tunneling devices. And we pay particular attention in terms of the metal contact as well with the channel material. So those are some publications featured here. Please take a look. So let's move to the electrochemical applications, which is the topic of today. So here's my outline. So I will give you a quick introduction about the 2D post-graphene material, PGM in short here. And we will talk about wet chemistry samples, how can they be implied in hydrogen evolution reaction, as well as lithium batteries. As for the CVD produced sample, we'll discuss how can we activate the Bessel plan using a backgate. So let's start with the introduction. So I think the PGM introduction can be simply put in the periodic table here. So if we look at the single carbon chemistry, we have a graphene, which is a well-known 2D material, right? So if we combine the transition metal with chalcogen, we can form transition metal dichalconide, TMD in short. And in today's talk, we will feature MOS2 as a representative example for the electrochemical application. Another class of the 2D material can be formed by combining transition metal and the carbon or nitrogen. All right, so it is known as mixing, and we will mostly discuss the titanium carbide in today's talk. So why do we care about post-graphene material? What is the difference between graphene and the PGM? So if we look at the previous slides, it is very clear, right? Compared to the single chemistry, single carbon chemistry graphene, TMD or MXTINs, they can have very rich chemical compositions. And therefore, you can really fine-tune the material property by wisely choose the element or stoichiometry. As for the structure-wise, the graphene usually shows the interlayer distance around 0.34 nanometer, while the titanium, the transition metal ditilectronide shows an interlayer distance of 0.65, maxing which is around 1 nanometer. Okay, so this enlarged interlayer distance is actually beneficial for ion intercalation, deintercalation, especially for the post-lithium chemistry. As for the band gap, as we can see, the graphene is a semi-metallic material. Everybody knows that. But for the band gap of the TMD, let's see MOS2 example, you can see the band gap actually changes upon thinning down the material. So especially when you go to the monolayer, you can have the direct band gap around 1.8 eV. So this is one difference. Another thing, of course, we know that we have a different structural phases for MOS2, which we will also discuss later in the talk. Sure, you can also conduct defect engineering, so on and so forth, to achieve the desired structure and property. So in addition to that, in terms of the surface determination, let's take Maxine as example. They have an enriched surface functional group, such as fluorine, OH, so on and so forth. Those surface functional group, making them highly hydrophilic, as evidenced by this simple picture. As you can see, the water droplet stays intact on the graphene-coated substrate, but on the Maxine-coated substrate, we can see the water droplet spread out, right? So such a property making this material very good to be processed in aqueous solution, and also advance the wettability of the electrode material, which is actually very important for electrochemical applications. So despite we have a lot of good publications and the field has moving significantly using the PGM for electrochemical applications, there are several issues that still exist and need to be addressed. The first one, let's take MOS2 as an example again. So it has low electrical conductivity, which will hinder the efficient electron transport and therefore the overall reaction kinetics. Another one is the restacking issue, just like the graphene, especially in the solvent process, all right? So such restacking will lead to the reduced interlayer distance and limited use of the surface area and active sites. So the last one I want to pinpoint here is the inert basal planes, especially for catalysis. So in order to increase the total number of active sites, we need to think of some strategy to activate the basal plane. And to address those three issues in this talk, I would like to talk about phase engineering and form hybrid structure to address the issue 1 and issue 2. As for the issue 3, let's talk about how can we engineering the catalyst support to activate the basal planes. All right, now come to my introduction. So finish the introduction. Now let's come to the wet chemistry synthesized PGM for the hydrogen evolution reaction. So I think everybody knows the importance of the hydrogen gas. So, well, this is simply putting in a way that we know that we have a shortage issue about fossil fuel, and we know that while using the fossil fuel, we will trigger the greenhouse effect because of the CO2 emission. However, for the hydrogen as an energy carrier, it has a very high specific energy, tripled compared to the fossil fuel. And also, more importantly, hydrogen actually can be produced through water. So that it is really the clean and renewable strategy to produce the energy where you don't have any carbon footprint in the process. So the hydrogen production basically involves the water electrolysis, and you can dissociate the water into hydrogen and oxygen. The respective anodic and cathodic reaction is listed here. And today we will focus on the cathodic part, which is a hydrogen evolution reaction, HER in short, okay? So in order to promote this HER reaction, we needed to have a catalyst applied in the system because we have quite a high activation energy for the water dissociation process. To evaluate the catalyst performance, people usually show this volcano plot where we have the exchange current density as y-axis and the DFT calculated hydrogen adsorption energy as the x-axis. And as we can see that the best material, which is known the platinum-based, noble metal-based material, they showed the hydrogen adsorption energy, which is close to zero, because such a medium interactions between the reaction intermediate and the catalyst will benefit for the adsorption and the desorption process. So this is important to have the ideal hydrogen adsorption energy, delta GH. So if we look at the MOS2, the theoretical predicted value is showing it actually surpassed most of the common metal and lies right at the bottom of the platinum group, indicating that the MOS2 has an ideal delta G, which can be used as a potential HER catalyst. So MOS2 has been implied, and there's a lot of literature in MOS2 for HER reaction. Of course, the benefit is that MOS2 is Earth abundant, and it has non-zero hydrogen adsorption energy, as we showed in the previous slides. But there are several issues we want to take a look. The first thing is that, of course, the 2D material has both basal plane and the edge planes, right? So in terms of the hydrogen adsorption energy, we can see the edge plane is preferable. So how can we increase the number of the active site? The edge site is one of the things we have to address. Another thing is that the MOS2 has two structural phases, right? Dominant two structural phases, actually. The 2H1 is semiconducting and the 1T phase is metallic. So as shown in this DFT calculation, again, the 1T phase showed favorable free energy for hydrogen adsorption. Therefore, we want to actually maximize the 1T content, the metallic phase in MOS2 catalyst. Sorry. So overall, the design principle for using MOS2 as a catalyst is that we want to have a highly conductive 1T phase as much as possible. And we want to introduce a lot of rich active edge sites. Of course, we have to consider the restacking issue and how can we prevent the 2D restacking, right? How to achieve this. So in this talk, I will discuss the strategy, which is using ion intercalation to trigger phase engineering and to form certain type of ternary structure. Here we have MOS2, maxing, and the CNT denoted MTC, okay? We form those ternary hybrids to address the above issues. So the ternary structure is synthesized by wet chemistry strategy. So basically, we have maxing, which is a highly conductive material, which can be used as a substrate for MOS2 to nucleate during the hydrothermal reaction. So we have titanium aluminum carbide, which is the parent phase of the MXene. We can remove the aluminum layer by simply acidic etching to obtain the titanium carbide MXene, and then put into hydrothermal reactor. And the solvent here we implied is a bisolvent, consists of DI water as well as DMF. So therefore, we produce this material as MTC. Here we also had a nanotube added in the system, okay? So the reason we choose the bisolvent for the synthesize is because we can have one T phase present from the 2H phase transformation. Then we label it as a dual phase MOS2, DPMOS2 here, okay? And I will discuss this one in more detail in the following slides. Another advantage for forms such as hybrid structure is that the MOS2 can be sandwiched in between MXene layers as evidenced in this SEM image. Therefore, we can prevent the MOS2 aggregation and the restacking. So the introduction of the CNT with the purpose of improve the overall conductivity. So we want to leverage CNT as a cross-link to across the 2D islands to further increase the conductivity of the system. So this TM actually shows more clear structures. So like you can see, we have MOS2 MXene islands and a nanotube actually bridging these two islands, okay, which can promote the universal conductivity of the network. And the interlayer distance was extracted from the TEM image, and we found that the MOS2 showed the interlayer distance, which is around 0.98 nanometer. Also, we have a lot of edge plane exposed through this white chemical synthesis method. All right, so in this slide, I'd like to discuss the importance of the solvent. As I mentioned previously, using the DMF, we can obtain the dual phase MOS2. This is evidenced by the Raman plot, okay? So for the MOS2, if you synthesize just in DI water, then you can obtain the clear E2G A1G peak, which is the feature peak of the 2H phase MOS2. But when we have the DMF in the solvent, what happened is that in addition to these 2H related peaks, we also can see the J related peaks, okay, G1, G2, G3. And also we have the E1G peak also emerged in the spectrum, which is related to the edge planes, okay? So if we take a look at this E2G, A1G to E2G ratio, we found the intensity ratio is around 2. Combining with the presence of the E2G mode, it's indicating the involvement of the edge planes in the structure. So the XRD also shows that synthesized MOS2 in DI water gave us an interlayer distance, which is around 0.64 nanometer. But if we have a DMF solution, then the extracted interlayer distance is around 0.98, okay, which corresponds well with the TM observation. So the large interlayer distance will facilitate the ion diffusion with an enlarged reaction area beneficial for the HER reaction. All right, so the presence of the 1T phase has also been found in the XPS measurement. So let me simplify this slide by highlighting the S2P spectrum, where we found that 1T phase ratio is around 66%, okay? So what is the mechanism for the phase transition? So when we have the DMF in the solution, during the hydrothermal reaction, it will decompose to form ammonia ions. Then the ammonia ion will intercalate into the MOS2, which triggers the interlayer distance increasement from 0.6 to 0.9, around 1 nanometer. And simultaneously, the ammonia ion will also have ionic interactions with the sulfur, which will stimulate the charging balance, eventually the gliding of the sulfur atoms toward 1T crystal geometry, eventually 2H phase transfer to the 1T phase. So another advantage highlighting the importance of using the bisolvent is that since we have titanium carbide mixing in the system, so oxidation needs to be seriously considered. So in order to suppress the oxidation, using DMF is very important. So this slide simply shows you that when we prepare the hybrid structure in the DI water, we notice that there's a titanium oxide nanoparticle on the surface, which is formed due to the presence of the titanium in the mixing. And also the oxygen atomic ratio is around 40%, which is very high. But if we switch to the bisolvent, where consists the DMF, we found the titanium oxide nanoparticle actually only a few, and also the oxygen content is much lower compared to the DI synthesized material, which is around 28%. So this is highlighting the importance of wisely choose the solvent for the white chemical synthesized. All right, so now let's implant the material and see what is its HER reactions. All right. So this slide features a few electrochemical measurement, and the first one is the LSV measurement, where we have a current density recorded while sweeping the potential. So the key factor that we can extract is the over potential value while achieving the current density around 10 milliamps per centimeter, which indicates how much potential or energy we have to input into the system to trigger the HER reaction. Of course, the smaller value, the better performance, right? So compared to CNT titanium carbide, which has a fairly almost no reactivity, apparently the MTC ternary structure showed the best performance compared to also the other binary or unary counterparts. So we also had the Tefel slope extracted from the LSV measurement, and we found that the MTC showed 51 millivolt per decade Tefel slope, which is the lowest in all of the material composites, okay? So this is the impedance measurement, also known as Nyquist plot. So 2 points that I want to emphasize here. The first point is actually the first intersect with the x-axis, and this point reflects the native electrical conductivity of the catalyst. Is known as series resistance. Of course, the lower the better. So MTC showed quite good performance here. And in another point is the diameter of the suppressed semicircle, okay? And this diameter is related to the charge transfer resistance, highlighting the barrier for the ion transport at the interface between your catalyst and the electrolyte, okay? Of course, the smaller the better. So overall, the MTC performs the best, okay? Turnover frequency, on the other hand, actually evaluates the activity per each active site. And apparently MTC also shows one of the best performance compared to the binary or unary composite. So the stability evaluation is conducted here. So we recorded the LSV curve before and after one sound cycling. And what we found is that the material performed quite good stability, and it is still maintaining 77% activity after one sound cycles with 72 hours continuously use. All right. Okay, so we also trying to understand what is the role of the CNT, okay? How much amount is the optimized amount that we should incorporate into the system? So from the label here, the number gets bigger, indicates we have a higher CNT ratio. And apparently, the MTC 100 shows the best over potential, one of the lowest Tefel slope, quite good charge transfer resistance, as well as series resistance, as well as TOF, okay, turnover frequency. So, of course, you would notice that the MTC 200, which is represented in this black curve here, has the lowest charge transfer resistance and also quite low, one of the lowest TFL slope as well among all of the composition ratios. But the overpotential as well as the turnover frequency is not as good as the MTC 100. What does that mean? So it means that if we increase the CNT content, certainly we can improve the conductivity of the overall network, promote the charge transfer at the interface between catalyst and electrolyte. However, because of the CNT has relatively low activity toward HER, and adding more CNT will significantly reduce the content of the MOS2. Therefore, the HER performance in terms of the overpotential and as well as the turnover frequency for MTC 200 is not as ideal as MTC 100. All right. So let me quickly move into the high performance anode based on the similar structure. So since we already had 66% of the 1T phase in the composite by simply conducting hydrothermal reaction in the DMF solvent, we wonder that whether or not we can continuously increase the 1T content ratio to further improve the composite conductivity. And on the other hand, since we introduced MaxIn to improve the conductivity, we have to consider the surface functional group impact on the lithium diffusion kinetics. So this simple figure shows that if we have the lithium ion, it can diffuse through this is fluorine functional group, or it can diffuse through some other pathways, either from titanium or from carbon, okay? So the theoretical calculation shows that, there's a quite a high lithium diffusion barrier if the lithium ion trying to diffuse through the fluorine spaces, okay? So it is important to control or reduce the fluorine content to further improve the battery performance. So based on the material synthesized before, we can simply conduct the emboli treatment where you have a lithium, we will produce enriched lithium ions through the emboli. Then this lithium ion can remove the surface fluorine functional group, which means it acts as a seeder to simply detach the cut off the bondings between the fluorine functional group and the MaxIn backbones. On the other hand, lithium ion intercalation will also trigger further phase transformation, and we anticipate and measured the 1T phase from the treated sample, and it shows around 72% of the 1T phase content, which is much higher than the previous result. So for the non-treated pristine MOS2 titanium carbide sample, we denote it as a PMT. For the treated one, we denote it as an MT. What we found is that we have a largely expanded feature in the emboli treated sample compared to the pristine ones. And also, the interlayer distance for the MOS2 doesn't change much, but somehow the MaxIn interlayer distance shrinked a little bit. This is due to the hydrogen gas generation and the heat production from the vigorous reaction between the emboli and water residues in the MaxIn samples. So the reduced interlayer distance from the MaxIn also indicates that we have a fluorine functional group removal. Of course, partially also because of the interlayer water evaporation. So this slide simply shows you we have this composite, and worth of noting that the fluorine the fluorine content from the pristine one is reduced from 11 to less than 1 point to emboli treated samples. Our Raman characterization also suggests the same thing. Basically, after n-body treatment, your 2H phase relative peak is actually decreased, with also the emerging of the J2 peak, which is relevant to the defect. And also, since the structure is more expanded, you can actually see more substrate of the titanium carbide peaks. In addition to that, the interlayer spacing extraction from the XRD measurement corresponds very well with our TM observations. So basically, with the n-body treatment, we have more 1T phase observed. Excuse me. So the XPS suggested that originally, excuse me, the original low fluorine content actually further reduced after the treatment, and the 1T ratio increased from the 60-something to 75%. And imply this material as a battery anode, we're expecting better performance with the n-body treated ones, and which evidenced by this capacitance cycle number curve. You can see the capacitance maintain a very good stability, which is around 600 milliamps hour per gram for the n-body treated sample at a current density of 0.1 amps per gram. But the pristine ones actually decays fairly fast. Also, the Coulombic efficiency of the n-body treated sample showed fairly good stability as well. So to evaluate the rate performance, we can see that the n-body treated sample showed quite good stability upon varying the charge current density. So indicating a better rate performance compared to the pristine ones. So now let's introduce CNT into the system, okay? So we have this ternary structure, and we have a relatively lower CNT content, which is 1551, some number indicating the lower CNT content. And the morphology characterization shows you here. And we have a higher CNT content in the system. But we noticed that with a higher content CNT ratio, actually this nanotube will be wrapping around the 2D islands. So the direct observation is that once you have more CNT, due to this wrapping effect, the ions cannot easily penetrate through and trigger the functional group, fluorine functional group removal. So we have a higher fluorine content in the higher CNT content sample. And simultaneously, our detailed XPS analysis also suggested the 1T phase in the higher CNT ratio is relatively lower compared to the one on the top, okay? So then we implied the relatively low CNT content ternary composite as a battery anode, and then we can see the significantly improved capacity, which is around 900 up to 200 cycles, and very good rate performance, which shows a specific capacity of 500 milliamps hour per gram, even cycled at 4 amps per gram. So indicating improved performance of the 2D material composite once you fine-tune the nanotube ratios. Now, let me move to the CNT growth sample, and how can we imply this sample to conduct fundamental studies for the HER reactions. So before we move into details, let me quickly show some of the CVD effort in the lab. So we use this two-zone CVD system and imply the transition metal liquid precursor to coat on the substrate and conduct the synthesis. We can produce a TMD with various different chemistry. So our recent effort is a collaboration with Dr. Hongyue Sun from University of Georgia. We're trying to use supervised and unsupervised learning method to help characterize the obtained CVD samples and trying to further optimize the CVD synthesized parameter. There are two papers listed here. Please take a look if you're interested. So another effort is in collaboration with Applied Materials. So we aim to really achieve the location-specific synthesis of TMD. So the strategy here is that we can intentionally create this pocket or window to load the moly precursor only at the pocket location, and then go through the CVD synthesize. So basically, we found that upon fine-tune the CVD parameter, we can produce a single crystalline, this kind of concave triangle, but also we can produce the round-shaped MOS2 flakes at the specific location. So considering that the MOS2 circular dot pattern showed a better location selectivity, so we are more interested in this one. And there are some characterization showing you this is a moly seed right after patterning, and some MOS2 growth, actually the arrays of MOS2 growth after CVD process. And the formation of MOS2 is evidenced by the Raman mapping, which shows the E2G and the E1G vibration mode here. So with the collaboration with Dr. Hua-Ming Li at UB, we try to evaluate the transistor performance of those circular dotted pattern. It's worth of noting that we do have this residue of the pocket, which is the moly oxide precursor during the CVD synthesis. So in order to evaluate the performance or the impact of the residue, what we did is we patterned the electrode finger at the bare MOS2 part directly on the silicon oxide. And also we pattern the finger across the pocket where you will have MOS2 moly trioxide, silicon oxide, moly trioxide, and then MOS2. So we evaluated this transfer curve as well as the output characteristics. What we found is that the on-off ratio between these two devices are actually fairly similar, which is around 10 to the order of the 5. And also this GDVD curve shows, linear behavior indicating this is ohmic contact. So based on the arrays of the MOS2 at a specific location, we produced these arrays of transistors and also conducted this statistical analysis. So overall, the best performing device showed the on current around 3 microamps per micrometer. Field effect mobility is around 20, and the on-off ratio can go up to 10 to the order of 6. So now let's come back to the CVD growth sample and how can we use them for the HER study. So first of all, I want to mention that using the wet chemistry process, usually we produce powder-like samples, right? Which means that you will have a coexistence of the edge and the basal planes. So in order to really determine the basal plane activity, it's going to be challenged due to the presence of the edge planes, right? So of course, there are some studies also used the CVD growth samples, but unfortunately, when you imply such a sample into the conventional 3-electrode setup, what you can not avoid is the, again, coexistence of the edge plane and the basal planes. Here's the result from this paper indicates that the activity of the MOS2 is more dominated by the edge length instead of surface area coverage. Again, indicating, this unavoided presence of the edge planes. So in this case, to precisely determine the basal plane activity, it is very important to create a new platform for electrochemical test. So here is our microreactor structure. So basically, we will have MOS2 on the growth substrate, which is silicon oxide, and we can pattern some electrode to connect MOS2, right? And then we will coat the PMMA entirely on the surface, only leave a small window to expose the desired area of MOS2 to be in contact with the electrolyte droplet. So the overall configuration can be represented by these schematics. So you have the window opened and then the water droplet dropped on top of it. Of course, the rest of the area is shaded by the PMMA, okay? And then you can have a reference counter electrode being in contact with the water droplet. And of course, the patterned electrode, in this case, titanium gold, functioning as the working electrode in the 3-electrode system. So what we found is that using this particular architecture, we can precisely confine the exposure area. So this is a really basal plane exclusive sample. So we patterned this sample with Thai gold as a contact. In the other word, the catalyst support. In contrast, we can also create a certain sample which only expose, relatively around the edge side. So this is a edge dominant sample. So our HER measurement, the LSV plot simply indicates that the edge plane exclusive sample showed, fairly high over potential, which is about 300 millivolt, and the edge plane dominant sample showed around 170 millivolt. So yes, from this particular example, we exclusively demonstrate that the basal plane did have a poor activity compared to the edge side, okay? So the next question is, how can we activate the basal plane? So if we take a look at this architecture, there's another, advantage is that we can leverage the silicon chips here and then apply the backgate voltage through the doped silicon and the silicon oxide stack. So in this case, we again conducted the LSV measurement, and then the overpotential plot, overpotential value can be extracted from the LSV. The TEFL slope can be extracted from this plot, and then we plot the value with respect to the gate voltage applied in this particular curve. What we found is that we can actually enhance the basal plane activity by simply applying the external stimulate, which is the backgate here. One more benefit of this architecture is that when you have MOS2 prepared in this particular electrochemical cell, in other words, the 4-terminal electrochemical cell, you can in situ exclusively modulate the electronic property of the MOS2 without preparing new samples. Therefore, you prevent the interference from preparing different samples, all of different surface areas, so on and so forth. So we can leverage this platform to exclusively extract the electronic property correlation with the catalytic property. All right, so why does the gate functioning this way to promote the basal plane activity? Well, for the HER reaction to promote hydrogen evolution, what we need to do is the Fermi level of the MOS2 need to be aligned with hydrogen evolution potential. And when we have the positive gate voltage applied, what happens is that we can shift up the Fermi level to approach the conduction band and with reduced Schottky barrier height for efficient carrier injection from the catalyst support, which is Thai gold here, to the MOS2 catalyst. So apparently, we can leverage the knowledge from electronic devices that certainly we can try different metallic contact to see how can we minimize the Schottky barrier and then promote the basal plane property. So this is the previous slide data showing you gold catalyst support where the basal plane showed fairly high over potential. But if we switch it to bismuth contact, we can see the performance significantly improved without applying any backgate voltage even, okay? So the value is achieving 160 millivolt, which is even better than the basal plane. So in the other word, with the basal plane support, with the bismuth support, the base plane can outperform the edge plane, indicating that the inherent catalytic activity of the basal plane probably is not inferior to the edge side as well documented in the field. So, all right, now let me move to my conclusion. To evaluate the potential of the 2D-based heterostructure in energy technology and boost their performance in practical application, it is important to prevent the layer stacking and forming a universal conductive network in the structure. So in this particular talk, we introduced ion intercalation as well as forming a hybrid network by introducing CNT as well as MXenes to be used as a catalyst for HER and LIB anode. So on the other hand, activation the inert basal plane can be achieved via enhancing the charge injection from the catalyst support to the active material by either using gating effect or just wisely choose the contact. So at last, I want to advertise the microreactive functionality, which is actually very unique and a powerful platform to exclusively investigate the correlation between the electronic property and the catalytic property. And then I'd like to thank my team members and all of the funding agencies to support our work. All right, thank you very much.
Thank you, Dr. Yao. Does anyone in the room or anyone online have any questions? No questions. Okay, it doesn't look like we have any questions, so thank you so much for your time.
All right, thank you so much.
Thanks, bye.
Bye, everyone.